Good morning, everyone. So it's my pleasure to have Jarosław Buczyński speaking to us about characteristic foliations on compact manifolds.
Thank you very much. Thank you for organizing this wonderful event. It was a great pleasure to come to Lausanne for the first time in my life. And then, well, thank you for coming to my talk after yesterday's dinner, which was a little maybe long for some people. So what I would like to start with, this is the last day of the conference. You might really not remember what was on the first day of the conference. So I will review a little bit of definitions and then tell you why I'm not really interested in precisely those versions of the definitions. So the setting that was typical during this conference was that we had some normal variety that we call it X. And well, in the original definition, it was an algebraic variety. Really, in some of the uses, it was analytic in some cases, or at least analytic manifold. And it's always over complex numbers. And we had a coherent subsheaf of the tangent sheaf. Well, that's a difficult word, but tangent sheaf. And then there were two conditions investigated by the speaker. So the first condition was that the quotient is torsion-free. The other was that the Lie bracket is closed for this subsheaf. And then in the columns talk, the first talk of this conference, we found out that we say that F is a foliation if both of these conditions hold. Then later on the same day in the afternoon in George's talk, we were told, but without actually writing it up on the blackboard, he told us that F is a distribution if and only if the first condition holds. So without the second, this is distribution. Every foliation is a distribution, but not the other way around. And then also on Tuesday, there was this thing that showed up, which is called characteristic foliation of a device of submanifold in the talk of Andre. So this is, well, there will be a very strong parallel between characteristic foliation in the title and the characteristic on foliation that appeared in the Andre's talk. And this is a simplified version of what Andre said and also modified to some extent, but this is the one that I want to refer to. So let's stick to that. So what I don't like about this definition, and I may have expressed my concern, is the assumption normal. So I will remove it. And now some of the properties that were explained to us by Kalum are now fail to hold. But I'm not concerned about that too much. And also, this definition includes two words that I find difficult. So if I was told to explain this to my master students, what is a tangent sheaf and what is a torsion-free sheaf, well, eventually I would succeed, but this will take some hours of preparation. So I want to get rid of these two words in the definition. So this word means tangent sheaf. The sheaf is an important part. And then the torsion-free. So this is what I'm going to do first. So I want to propose an alternative, well, not propose, but state an alternative definition of foliation and distribution. And it's in the setting of normal varieties, it's equivalent. So let me just white chalk maybe.
There's more over here.
Oh, thank you. So I'm looking at the, again, I don't want to use the word tangent sheaf, so I want to use the word tangent bundle. So this will be denoted TX. So in order to have this, I need X to be smooth, or I need to restrict to an open subset inside the smooth locus of X. And inside here, I'm looking at the sub-bundle. Now this is a sub-vector bundle, Fu. And now I want to say that the distribution for me is an equivalence class of pairs so I want FU and U, or maybe the other way around. Maybe it will be better the other way around, such that FU inside TU is a sub-bundle, sub-vector bundle. And U is a Zariski open subset. In smooth locus of X. Oh, and the equivalence is the one that you can guess, that FU, a pair FU and U is equivalent to a pair GV and or FV, well, DV and V, if and only if, well, the restriction to the common intersection, Zariski open dense maybe, so that we don't say that I can take empty. That the intersection FU restricted to the intersection U intersected V is the same sub-bundle as GV. This is U, this is V, restricted to the same intersection. And this leaves in the tangent to U intersected V. Okay, so let's, why do we need an equivalence class? Well, this is for the purpose of extending. Well, so first of all, there is always a maximal set for which this will be defined. This is just the union of sets in the equivalence class. So there is always exist U max, which is in the old definition, it's the regularity locus of F and X. So it's a locus where both X and F are regular. And well, the equivalence class is designed in such a way that if I restrict my foliation, I can do it on one equivalence class, and then I can, for free, it's automatically by equivalence class gets extended to the maximal locus, which might be larger than the restriction of the original locus. So if you want, I can give you an example, but I think you have seen these examples, this kind of examples on the other lectures. I don't know. Do you need an example for that, or you remember?
What about the singular, the type of singularities?
I'm not assuming anything about any type of either F or the what do you mean? What are accidentals? The
X plus exponential of x1.
dx.
I mean just the sub-bundle. What about the extension?
I'm right. So we are talking on different, I think, levels. So either you want analytic things or you want algebraic things. So if you want algebraic things, then I want this bundle to be algebraic sub-bundle. If you want analytic, then I don't mind bad singularities, analytic bad singularities. Is this satisfactory for you? But what I'm interested is really an algebraic setup, which once in a while I will restrict to an open neighborhood in analytic on an open neighborhood. So I should have made it precise. So when I say algebraic versus analytic, well, either all is algebraic or all is analytic, right? So the closure of F, if we are in the algebraic setting, yes. That is probably correct. I need the assumptions about singularities, which I said in the singularities of both X and F, then they are becoming equivalent. So this one is slightly more general, allows more freedom, worse singularities than the original definition, but in both F and X. But in the setting that was originally presented to us, they are equivalent. So algebraic varieties and normal algebraic varieties, they are equivalent. So so this is the definition that I want to work with. And in fact, I will, for some technical reason, I will need a little bit more complicated. Well, of course, one more thing, a foliation is a distribution that satisfies two, right? Now the sections are taken over any of the vector bundles Fu. And then I want to have a more general definition. So a distribution on E, a vector bundle. So I start with X. I want E to be a vector bundle on X. Now X can be singular, but the vector bundle on X is just locally trivial, so there is no problem with singularities of X. And then a distribution on E is an equivalence class of pairs. Well, there again, it will be Fu and U, such that Fu is a subvector bundle of E, and U is some Zariski open subset, open dense subset in, I don't need smooth locus anymore. And then this is again the same thing in E restricted to U. Then here I have EU. Okay, and then why I need this? Well, there are some reasons for that. So what I will do in a second, I will work with a divisor. And then, or some submanifold, or generally submanifold or subvariety of some variety. Then I want to look at the distribution, which is Tm inside Tx restricted to M, and then perform various operations on this particular distribution. So I want to look at the distribution on M, but inside a larger vector bundle than just M, and that will become clear in a minute. So so is this generalized definition clear enough, or should I explain something else here? This is let me say that this is not really my approach. This was developed, well, probably also based on area works, but I've learned this from Junmook Huang, and this is kind of, I suppose this is well established in the literature. If you want some references, I can provide it after the talk. And okay, so now I want to introduce holomorphic. Well, I hope it's not a new notion for everyone, but as a motivation to study contact manifolds, one of the motivation is the analogy, something that's more familiar to many people. These are holomorphic symplectic manifolds. And then this is a smooth algebraic, but not necessarily algebraic. Typically, it's assumed to be algebraic manifold over complex numbers. And then with a two-form omega, the holomorphic two-form, such that omega restricted to each point, at each point omega x is nowhere degenerate. And the omega is 0. Well, it's no degenerate for all x in X. So this is an analog of the symplectic manifold in real geometry. This is also something that naturally appears in classification theorems from the point of view of either Riemannian geometry or from the point of view of the classification of varieties with trivial canonical class, because at least the projective case, not requiring X to be projective here. And this is, well, of course, you can forget algebraic, you can do it analytically as well if you want. And well, it's something that people study a lot. Now, the point is that we have this two-form here, and it helps a lot. So in particular, this two-form, because it's non-degenerate, it determines an isomorphism between the tangent and cotangent bundle. And then the thing that I want to stress, this is the characteristic foliation, which can be phrased for all sorts of subvarieties of X, but I will just focus on the case of divisors. So I pick a divisor. And here is the thing that this is, well, by this I mean a codimension one subvariety of X. And the problem that I had, the technical problem that I had, which forced me to look at this generalization, is that I have no idea in the application that I want to explain. I have no idea if D has descent singularities or not. This is constructed in some geometrical way. And I can understand it generically, more or less I know what it is on the generic, around the generic point. But at the special point in codimension one, there's absolutely no control on the theory has absolutely no control on the singularities and things. And in one case, I even know explicitly that it's not really a normal divisor. So so that's why this whole generalized setup is slightly more, it's necessary for by consideration, slightly more convenient as well. And in this case, I want to look at the foliation on D, which is defined as a T, the tangent space. I take the tangent space to D. Now I want to take the perp of this tangent space with respect to the omega, so the set of vectors perpendicular with respect to omega to everyone in the tangent space. And this, it's not difficult to see that in the divisor case, this is contained in the tangent space of the smooth locus of D. So what I get is a foliation. Why is it a foliation? Well, this is because it's just rank 1. So this, if this is 2n dimensional, this is 2n minus 1 dimensional because it's a divisor. So the tangent bundle has rank 2n minus 1, and this guy has rank 1 generically again. With this over, well, for smooth locus, it's okay. So this is my, then this is my characteristic foliation of D. Okay, so that's the symplectic version of the characteristic foliation. And well, I should just say that this appeared on the talk on Tuesday by Andra in slightly more general version, and not over complex numbers, but over real numbers. So on symplectic manifolds, not on holomorphic symplectic manifolds. And then, well, we've seen some good uses of that. So I will leave it at this point to just say that this, you already know this is an important notion. Okay, so I don't have to justify why I'm introducing this definition. Okay, the next thing I want to explain is the final difficult word in my title, which is contact manifolds. So now I will switch to a different letter, maybe Y. Y is a contact manifold. So I'm first of all, I want it to be and let me stress, I mean that I mean complex contact manifold. So this is again algebraic or analytic, like or analytic manifold over complex numbers with a regular distribution so by regular, I mean that in the equivalence class, there exists a pair of that includes Y, the whole space Y of as one of the open subsets. So it's I can extend it to the whole tangent space of Y. And then I want this to be a regular distribution with rank F equal to the dimension of Y minus 1. And I also want that the quotient, which now is a line bundle because of this two conditions, that this is regular and the dimension. I want this, well, locally defined one form. So this is a twisted one form. So locally, it's just an honest one form. I want this to be non-degenerate in the following sense, that if I take the derivative of this one form on some open subset in some coordinates, and then restrict it to wedge 2 of F, which is just, I only consider this form to be defined on F, then this is nowhere degenerate. So this is the analog. This d theta would be the analog of the symplectic form, but we have one dimension more. So in particular, this guy has some even rank, and then this guy has the dimension of Y in particular is odd. So maybe I should stress then that this thing, so whenever you have some distribution, you can always define this, and this is actually equal to the Lie bracket restricted to F, and then take a modulo F. So in other words, we take two vector fields, tangent, local vector fields tangent to F only, both tangent to F. We take their Lie bracket will might stick out of F. So unless this is a foliation, it will stick out of F. And then we take the quotient, and it turns out that it becomes a well-defined map of O of X modules. So the theta restricted to wedge to F is an honest map from wedge 2 of F to L. It's a map of vector bundles or map of coherent Y modules. And then so if this map is identically 0, we are back in the situation of foliation. So this is equivalent to the condition 2, because this will say that the Lie bracket of things that were tangent to F, modulo F is 0. So this means that the Lie bracket is contained in F, which is the same thing as saying that this is a foliation. Okay, and then this is kind of opposite case of foliation. It's nowhere degenerate. It's as far from being foliation as possible. So the contact manifolds are the geometric object that I'm interested in, essentially since the beginning of my master's studies. And so what I want to look at is the analog of the characteristic foliation in the case of divisors on contact manifolds. So this can be explained in two equivalent ways. So maybe I will stick to one of them, which actually stays on Y. So I have my Y and F is the contact manifold with the contact distribution F, and inside Y, I pick a divisor, D. Again, I have no control on the singularities of the divisor, so so even though Y is smooth, D can be arbitrarily bad. And then D, I can take the tangent bundle to D, at least wherever it's defined. And then I want to intersect this with my distribution F, again, on this restricted to the set D0, but I don't mind because F is a distribution. So in an equivalence class, there is a subset. There is FD0 in particular. And this is a subspace of F now. And in F, I have my two form, d theta restricted to F. So I can take the perpendicular with respect to this two form. And now what I get is, well, so you see, now I'm really exploiting my notation, because this, well, maybe I should go one step back. So this is not necessarily a vector subbundle of the D0. This is some subset, but there is an open subset here where this is a vector subbundle, right? So there could be points where D is tangent to my distribution F. And then the intersection will have no expected dimension. It's not true everywhere, because otherwise F would be a foliation, at least on this divisor D. So the D would be an integral divisor, and this contradicts the non-degeneracy condition. But there is some smaller subset. So I would need, so if I was using the original notation, I would probably need to do a lot of restrictions, but I'm happy because this is this is some foliation, some distribution defined on some open subset. I don't care what exactly the subset is, right? And I can make operations on this set. And now inside here, I can also take the perp with respect to the theta restricted to F. So then again, I might need to reduce my open subset, but generically it's going to be a line bundle in some on some open subset. So it is this guy here is a characteristic foliation on D or of D on Y. So whenever you, well, in other words, whenever you have a divisor in either symplectic or contact manifold, you can do essentially perp of this of the tangent space of this divisor, and you get some nice, well, natural defined foliation in each case, one-dimensional foliation. And then it's going to be really, it might have really bad singularities. So the both D and the foliation has not well. Things can get very wrong. So even in the simple cases, if you take some nasty divisors, then what you will get might be not integrable. So already, if we take C2n as a symplectic manifold, or the corresponding contact manifold with some theta going from P to n minus 1 to O of 2, then you can take a quadric here. So there is a 2n minus 2-dimensional divisor of degree 2, with corresponding quadric cone. And depending on which quadric you take, even smooth quadric, but so the generic one, for generic one, the characteristic foliation will be the transcendental, so the leaves will be dense. And then for special ones, the leaves will be very nice. Well, so what I mean by special and non-special. So you see that I'm choosing both omega and the quadric. So there are two forms involved. So one is an alternating two form, the other is symmetric two form. And the group preserving one will not act transitively on the set of the others, right? So there will be different orbits, and so the generic orbit, for generic orbit, the characteristic foliation of D will be transcendental, we have dense sleeves, and the other guys, for the other guys, it's actually very nice, and it actually are orbits of something, some subgroup, some nilpotent or some one parameter subgroup acting on them. So it's essentially the same choice as if you had the Lie algebra SP to n, and this maps exponentially to the B group XPN, and you pick a line here. So you can associate the choice of the quadric with a choice, maybe L is not a good word, maybe L, lowercase l. So a one-dimensional linear subspace of this. This is a Lie subalgebra, so it will exponentiate to some Lie subgroup, so to some subgroup of this SPN. And if it's closed subgroup, then the orbits will be, then the leaves will be the orbits, and it will be nice algebraic, but otherwise, if this is not closed subgroup, if this is something that whose closure is much bigger, then the leaves also will be much bigger. So roughly, this is the correspondence here. So the characteristic foliation is something that's typically bad. And for some reasons, the naturally constructed geometric divisors on my Y that I came across in my life turned out to be integrable. So they turned out, sorry, not integrable, algebraic. So the leaves are actually nice curves. And this is some phenomena that I have not yet understood why this actually happens, other than in those cases that I managed to understand. So I understood it in the two cases that I want to briefly explain, and that's the topic of my talk. So what I have here is this contact manifold, and maybe I should say a few words about the things that we know so far about contact manifolds. So there is a huge conjecture, maybe theorem, maybe first theorem, and theorem is motivated by the conjecture. I will say later on what's left after the theorem, and there are many names here. Maybe I should mention Quebecus, Paternel, Somerset, and Wiśniewski. And then I should mention also Demailly, and I should mention well, some other works by Quebecus, but let's not let's just leave it here for now. So the theorem says that if Y is a projective contact manifold, then, well, we have three cases. Then either, so case one, Y is a projectivization of the, well, I guess here I should say tangent bundle of some M is a smooth projective smooth projective algebraic variety. So the tangent or cotangent, depending on whether you are using Grothendieck or classical notation. So this is Grothendieck. So if you're interested, so this is the hyperplanes in the tangent space. So it's something that has a rational map from the star of M. And it's not an accident that this is a classical example of a symplectic manifold. This is exactly why this happens. Oh, -0 section. So this is one case. This is what classically known. The other case is P2n+1. I should say contact manifold of dimension 2n+1, projective of dimension n+1, and then in this case there is an important distinction between this case and the next one. The L, which is the quotient of the tangent bundle by the distribution, is the O of 2, or Y is Fano, and the Picard group of Y is generated by the class of ample line bundle L. So you see that's why I split it these two cases. This is also a Fano manifold, but the tangent by the Picard group is not generated by the thing. And the conjecture says, well, conjecture was before the theorem. Conjecture was to classify all projective contact manifolds, and it expects that it's either this guy or it's a homogeneous space. So what's left from the conjecture So the conjecture is attributed to Lebrun and Salomon. And according to the rumors I've heard, Salomon insisted on conjecturing it, and then Lebrun opposed to that in their joint paper. So they didn't really write it as a conjecture, but they wrote a paragraph. It is expected that this happens, right? So it's, well, and then after that, everyone says it's a conjecture of Lebrun and Salomon. So at least this is what I was told by some other people. Okay, so the conjecture is that in case 3, it's what's left from the conjecture. Y is equal to G mod P for a simple Lie group. G, and then P is a very specific parabolic group. So there is unique parabolic group for each G, which comes from the adjoint representation. P is a parabolic. So it's known in low dimensions. Maybe I should mention Stéphane Druel in particular did the conjecture in dimension 5, and then it's actually enough to prove that Y is G mod P for some group G and some subgroup P, because then again work of Beauville takes care of the rest. And I should say that if there are 2 types of groups, so if G is of type A, meaning it's SLN, then you actually end up in this case. So, okay, it's a contact manifold, but it's not in this case. So G is not equal to AN. And also if G is equal to CN, type CN, which is symplectic group, then you end up in this case. So you don't really want these 2 simple groups included in the conjecture anymore. So I think this is more or less the motivating conjecture. And now, my main motivation to state this theorem is that I want to assume this 3 for free. So that, well, the things that I'm going to say have slightly different behavior in these 2 cases. I want to stick to the case 3 so that I have more freedom to not go into all the details. Okay. It's not so easy. So, what the divisors that I want to construct come from union of some special curves. So I will look at curves C inside Y such that, well, first of all, C is a rational curve. And second of all, L restricted to C, well, L intersected with C is the intersection number of L and C is equal to 1. So L, I remember this is always this, if we had contact distribution in the inside tangent space of Y, this was the global distribution, so a regular distribution. So the quotient is an honest line bundle, and L is always this particular line bundle. So for contact distribution, there is line bundle. And we already know this is I should say that perhaps here that we always have that ky. This is some easy calculation from this exact sequence, and the contact form ky is isomorphic to O, well, or maybe O of ky is L tensor n plus 1 dual tensor n plus 1. So in particular, the Fano case means that O of that minus k is, so maybe I will move the dual here, so that this guy is ample. So L is ample in our case. So this is a easy calculation. So independent on the theorem. But in particular in the third case, canonical device, we have a Fano manifold, which is with this L line bundle L ample. So in particular, we always know that this number is positive for all possible curves, but we are looking at the special rational those rational curves that have intersection 1. Since and now the general nonsense about Fano manifolds of such high index will tell us that this such C always exists, and in fact they cover X. We are in case 3 because case 2 is an exception to always, right? So such, and we call those so such curves exist in abundance. So there is a moduli of dimension something like 3n plus 1 or 3n minus 1 exist, cover X, sorry, cover Y, and are called lines. Oh, surprise, intersection number 1, lines.
A1 and Cn, sorry, it's An and Cn. So do all the other ones agree to contact structure?
Yes. So whatever. So whatever simple V group you take, it's slightly more than that. You can take the max. Well, you can take its action on its projectivized adjoint algebra on this adjoint representation, projectivize it. And then you have minimal orbit, which is smooth and projective, and its contact. So also in this case it's An and Cn, but these two fall out in the other cases. And there is more behind that, but I guess we can discuss this later. Sorry, what's minus ky is very ample.
It's true for it. If the conjecture is true, it should be true.
So minus ky, yes. So if the conjecture is true, then L is already very ample. If L is very ample, then we know the conjecture. So if assuming that L is very ample, this is the conjecture is true. I don't know if assuming this ky is very ample gives you any information that helps. I'm not aware of that, and I think it's definitely unknown, and I never seriously tried, but I tried with like twice L being very ample, which is more than just ky being very ample. So it's subtle. Right, I'm not sure I will take, so I will just, there are, so it's the intersection numbers, well, you have seen minimal model programs, so you're not surprised that various intersection numbers, the degrees and so on, will tell you the dimensions of some moduli spaces of curves, right? So you have deformations of such lines, and there are the people studied a lot of these deformations. So what happens is that it can be shown that for all all y in y, the set, well, maybe let's say there exists, well, there is the family of lines through y as pure dimension in particular is non-empty equal to n minus 1. So the dimension of y is 2n plus 1. So now we can take the locus cy inside y. For each y, we can take the locus, maybe c is not a good letter, maybe curly c, locus of all those lines. I mean, this is a theorem, right? I'm not saying this is trivial, but you have seen in Mori theory a lot of calculations of dimensions of moduli or estimations of moduli, dimensions of moduli spaces. And if you prove that something is unabstracted, which is the difficult part of the theorem, then you will get something like that. And that's what Quebec was done. Well, Quebec was done, but basing on some previous things as well. Locus of all the lines through y. And this will, again, it's a theorem, but this one is not so difficult. So dimension of cy, again, is pure, and it's equal to n. Pure meaning that each irreducible component has dimension n. So, well, so this is far away from being the divisor, but so divisor will have the dimension twice this number, right? So what we were going to do is we are going to do the union of all cx for all x in cy. Since, let me draw it. So we can take, so we have our manifold y. We pick a point in this manifold, any point, doesn't have to be generic. And then we draw a cone of lines through this. This is of very small dimension. And then for each point of this cone, we again draw a cone of lines through this point. In other words, we define dy to be the set of those z in y such that z is connected to y using two lines. I will draw it connect in this way. So connected to y using two lines. And it turns out that this is a divisor. So the proposition, and this is actually, I think, the first result of mine in this direction is that dimension of dy is equal to 2n. Again, pure. So every irreducible component is of this dimension 2n. So I can do a characteristic foliation for that. This is a divisor. How much time do I have? I have 3 minutes. So, so characteristic foliation. The theorem. Well, one theorem is that the characteristic foliation of dy is tangent to the second lines. So whenever I have dy, it turns out, and for a general point z, this again is only true generically. For each general point z, there is a unique. It turns out that there is a unique line connecting. There is a unique pair of lines connecting y and z, and this characteristic foliation is exactly tangent to this second line everywhere along this line. Well, generically along this line. So you have point y, you have some z1, z2, z3, and along this line, the foliation is the tangent space to this line. Along this line, the tangent space is this thing. And since these lines sweep out the whole divisor, then this is actually defines the whole foliation. Well, there will be singularities, both of d. I have no control on singularities of the variety d, and I have no control on special points along this line where this happens. In particular, the whole cone, the whole original cone, this one will be in the singular locus of d, and then I have no control on the foliation or its singularities along the spaces. There was one more divisor that I wanted to present, and then the result was more or less the same. I should say that this was not just the foliation here was a tool. My time is up, so I don't have time to explain the final result. But since this is a conference of foliation, I think you will be excited to know that the foliations are actually being used in geometry, not well in something else than you've heard before during this week. I mean, we've heard a lot of applications of foliations. We heard a lot about classification of foliations. Well, I wanted just to contribute to throw in another geometric theory where foliations naturally arise. They provide some nice results, and I mean, this is about one-dimensional foliations, but there are some other, well, there are also dimension n foliations appear naturally in some special cases, and this is part of a bigger theory. I would like to thank you very much for your attention, and that's it. Thank you.
Great. So any questions?
So can you present the second result?
Okay. So the second result is a little bit subtle. So there was, well, I should say a little bit about I swept under rug the pure dimensionality of here. So there are some choices that people believe that if you restrict this, well, so you have a space of all rational curves of degree 1 with respect to L. And then this space potentially might have several irreducible components. In the examples that we know from the conjecture, so if we restrict to the cases not AN and not CN, there is always one component. There are two components in this case, and there is 0 components in this case. And then people would like to know that if we pick one of the components, so they are not so much bothered how many components are there, but Huang and Quebecus would like to know, in particular them, if we pick one component, is this set, the set of curves from this component, is it irreducible or not? And then there was a paper, and there is a paper with a theorem in there that says it is irreducible, but the proof is incorrect. And I was trying for many years to fix the proof. And then the reason this is, it's exactly the issue from which I started from, is that if we can assume that the certain divisor, so there will be a divisor, there might be a divisor that things go wrong. There is like a branching divisor which will guarantee that this fiber is irreducible or not. So there is a divisor. I will phrase it. So maybe general line as EY restricted to C. So the general line C is smooth, which means isomorphic to P1. And then this means that the tangent bundle has this very special splitting. There are a bunch of zeros. There is a bunch of ones, and there is 1, 2, which is the tangent space to the lines. And this is the kind of a standard splitting for, I think this already appeared in some lecture about minimal model program. I think it was in Paulo's lecture, wasn't it? For another context, well, never mind. So this is the standard splitting. So now if we take the inside the moduli space of curves, consider the set of curves with other splitting, so non-standard splitting. So, well, now if this set is not, if of codimension at least 2 in the set of all curves, then the CY, general CY will be irreducible. If not, then consider locus BX, no, B inside Y, which is the union of all non-standard curves. So there are some statements that are quite correct. First of all, it doesn't feel Y, so a line through a general point will be we always have this standard splitting, so it cannot fill in Y. And if there are many of those, this will be a divisor. Now, what Quebecus showed, well, Quebecus was claimed then even if this guy is a divisor, he can prove that CY is irreducible. But it turned out that along the way, he overlooked the possibility where B is not normal. So if B is normal, if B turns out to be normal, then his proof works fine. But assuming that B is not normal, it turns out that this becomes an interesting divisor on Y, on a hypothetical Y, which, if conjecture is true, doesn't exist, but we don't know it yet. And then this divisor, so this divisor is again a divisor, and we can take the characteristic foliation of B, and it turns out that this is tangent to some even more special curves. So there will be 3n-2 dimensional family of curves here, but there is inside here, there is 2n-1 dimensional family of curves, which are tangent to this foliation, characteristic foliation of B. And they are not only non-standard, but they're actually also singular. So this might be a little weird to you, but there are singular lines in this word. Well, and they're really bad. And what I managed to prove using this foliation and another foliation is that B is actually, if we normalize B, it's a projectivization of some vector bundle of rank where E is a rank, rank n+1 bundle over some variety Z of dimension n. But that's the normalization map. And then this guy is normal. It's well, we didn't manage to finish the proof yet. It's nice geometry, and it actually uses a lot of foliations, the proof, but it's kind of not something that you want to present on the blackboard. Not doing a limited time talk, right? I mean, if you had 3 days for discussions, then I could do that.
Any other questions? With that, let's thank Jarosław again.
Thank you.
Two important announcements. The first one is we have to return all of these. So I know that we were all looking forward to keeping them. But so if you could leave them